Okay, everyone, we will start it here and let other people join in between. So, hello everyone, welcome to the GATE NPTEL lecture course. Today we are going to study magnetic field and vector potential due to a solenoid, and then we will solve some questions based on this concept in previous GATE year question paper. So, with this thing, we will start it. So, I think you are all familiar with this concept of magnetic field due to a circular coil, as I have told you in the last class. It is very much like the magnetic field created by a magnet. So, if you wanted to calculate the direction of the magnetic field due to a circular coil, for example, consider this case here. Your current is flowing in this direction. Then the magnetic field at the center of this coil can be calculated by right hand rule. You have to curl your finger in the direction of current, then your thumb will give the direction of magnetic field. And if you wanted to calculate the magnetic field at some other point, basically you have to consider it as a small segment, which is like a straight line wire, and then you have to just um, kind of hold this wire in your right hand with your thumb give the direction of current, then your finger will give the direction of magnetic field. So if this is the current due to a single circular coil. So if we take a large number of these coil and we place very close together such that the magnetic field due to a one coil. So if this is one coil, then the magnetic field which is created by this one coil, then if we place another coil very much close to this coil, then the magnetic field will just add up. And in this way, if we place a very large number of these coil, then we will create a very strong magnetic field along this direction compared to this outside direction. And this magnetic field is very strong as well, depending on how many numbers of coils we have used. So basically, solenoid is this combination of this circular coil into the form of this spring, and they are very close together such that the magnetic field is almost a straight line within this inside the solenoid. And this magnetic field is very strong and it is uniform as well. So solenoid is used to create a strong uniform magnetic field by combination of this circular coil. Sometimes we can also consider the solenoid as you can think of a cylinder in around which we have wrap a aluminum foil on which a surface current K, which is equals to Ni, and is the number of turns per unit length. And this surface current is flowing across this aluminum foil. So it is the simplest representation to represent a solenoid, and basically this representation is generally used to in most of the calculations. So this is the basic pictures of the solenoid. Now we have to calculate what is the magnetic field due to the solenoid. We have two cases. One is inside the solenoid and another one is the outside part. So we have to calculate magnetic field in both area, inside as well as outside the solenoid. First thing intuitively that come to our mind when we think of calculating the magnetic field due to the solenoid is use the symmetry property and then use Ampere's law to calculate the magnetic field. But to allow the Ampere's law, we have to calculate this integral. Close B integral dot dl vector equals to mu naught In close. So we have to consider an Ampere loop along which we will take our dl vectors. So we have two cases here. We can consider the Ampere loop as symmetry permit to us in circumferential direction, or we will take it in another direction. But if you take the Ampere loop in the circumferential direction, then your dl vector will be along the circumference direction. So if you are considering the cylindrical coordinate system, this is your z cap direction, then this direction is the phi cap direction. So your dl vector will be in the phi cap direction and your magnetic field in the z cap. And when you try to calculate this integral b dot dl, basically you have to multiply mod b naught. B dot dl means mod b vector mod dl vector into cos of angle between B and D. And Z and phi will contain an angle 90 degrees cylindrical coordinate system. So basically, your integral will become zero automatically. So we cannot take the circumferential loop in this case. So the another possibility is we will take the rectangular loop. So when we take the rectangular loop, we again have two possibility. We can take completely outside it when we calculate the magnetic field outside, or we take half inside or half outside, something like that. So let's consider this case. We take the completely outside amperial loop, and in this case, if we wanted to calculate the magnetic field, I'll line integral of P dot dl vector, then we have to take integral along this closed loop. So we have to integrate from P to Q, then Q to R, then R to S, and then S to P. And then we will form this closed loop along this line integral. So we will separate this integral into four parts. So one P to Q, then Q to R, R to S, and S to P. Now, if you look at this Q to R, this is perpendicular to the magnetic field. And similarly, if you take P to S, which is again perpendicular to magnetic field, which is, as I have told you, from this analogy of circular coil, the magnetic field in Z direction. So if we calculate B dot dl for QR, this is going to be 0. Similarly, for P to S, this is going to be 0. And the direction of current for P to Q is opposite to the direction of current from R to S. That means B dot dl, if we calculate for P to Q, it is cos 0. But if you calculate for R to S, it is cos 180 degree. That will give one negative sign here. So we have the magnetic field from P to Q and R to S. Now P to Q is at a distance of A from the axis of the solenoid, and R to S is at a distance B from the axis of solenoid. So magnetic field at a distance A and magnetic field at a distance B is equals to mu naught I enclosed from Ampere's law. There is no current inside this loop. You can see the current is in this region of solenoid. So basically I enclosed is 0. So magnetic field at the position A is equals to magnetic field at the position B. That means if I take A and B somewhere like this, I will take my A point here and B point here, or I can take at infinity as well. My magnetic field will not going to depend on the distance since BA is equals to B. So since my magnetic field does not depend on the distance, so it will be same as whatever the magnetic field at infinity. So we can take it like B at A is equals to B at E and B at infinity, and which is we already know from this line property of magnetic field that these lines will kind of become at a larger separation, and therefore weaker the magnetic field. At infinity, the magnetic field will become more of a zero. So we can consider that the magnetic field, if we are considering the outside region, it is always going to be zero. Now consider the another case when we have the magnetic amperial loop half inside and half outside. In this case, we again consider we have to again calculate closed integral P dot dl, and Q to R and P to S is again going to be 0 since magnetic field is 0. Now the important case is this R to S. We have already calculated that the magnetic field outside field is 0. So we have left with only Q to P. Let's say the length of this loop here is L. So when we calculate this P dot dl here, it will be dl, and it is due to this P to Q. All other consider case are 0. So we have B to L mu naught I enclosed. Let us consider that within this L region, the number of turns that is coming inside this loop is N. Therefore, the total current will be N times I the current that is flowing in one loop. So B into L will become mu naught Ni, and B is equals to mu naught N by Li. If we take N by L as number of turns per unit length by a small n, then the magnetic field due to the solenoid is mu naught Ni. It is in Z direction from the magnetic field lines property inside and it is zero outside. So this is an important formula that you have to remember whenever you try to solve questions that are based on solenoid. Now there is a special case as well. If instead of taking the string, in like x direction in straight line, we can take it in mold it into the circumferential direction. And if you take the just one loop and try to calculate the magnetic field direction, it will add up like in the circumference. So here the magnetic field will be in phi cap direction. So our magnetic field become phi cap and our total length, which is initially L, now it will become 2 pi r, which is the total circumference here. So your total length will become 2 pi r, where r is the radius from the center of this springs. So magnetic field due to this toroid case will become mu naught Ni by 2 pi r. I just put the value of L. And the direction of magnetic field is phi cap. It is inside and zero outside. It's just a special case of this solenoid. So basically the thumb rule is whenever you try to implement this Ampere's loop or whenever you try to calculate this kind of integral like A dot dl that we will encounter later or close line integral of P dot dl, always try to make your Ampere loop such that it will take the form like mod of P mod of t cos 0. That is, try to make the Ampere loop in the direction of this field vector, and that will make your angle cos will be 0. So if this will make your life much easier whenever you try to solve the questions. And we will see whenever we calculate this A dot dl kind of thing, how we are taking the Ampere loop in this case. So there is also a special case whenever the length of the solenoid is finite. Remember we have done in the last class, we have calculate the magnetic field due to a finite length wire. Similarly, here the finite length solenoid, if it make an angle phi 1 with one end and angle phi 2 with the other end, and L is the total length of the solenoid, then the magnetic field will be mu naught Ni by 2 sin phi 1 sin phi 2. And the field that we have calculated earlier, in this case, the length is infinite. And if you increase it to infinity, phi 1 will become mod of a pi by 2. And similarly, if we increase here in this direction, phi 2 will become pi by 2. So this quantity will become 1 and this will become 1. And magnetic field become mu naught Ni inside the solenoid. So the case that we have calculated earlier. So this is the general formula for the magnetic field of finite length solenoid. Now let's consider the case of vector potential due to this solenoid. So before going into this property of vector potential, we already know that to calculate the vector potential, we are going to use this formula. Magnetic field B is equals to curl of A. And when we take the surface integral on both sides, it will become P dot dA, surface integral of this vector. And when we apply Stokes theorem, this integral will become closed line integral A dot dl. So basically, we have to use this formula, closed line integral A dot dl equals to surface integral P of P dA to calculate the potential vector A. So again, we have to consider the Amperian loop here. So we have to know what is the direction of this A vector should be. So the direction of this vector potential always in the direction of the current. So in this case, the direction of current is circumferential. So we have to take the direction of vector potential as circumferential. Therefore, our loop will be is in the circumferential direction. So that whenever we try to calculate A vector dot dl, it will become mod A into mod dl and cos of 0. So only this quantity will remain. So whenever we try to calculate A dot dl, in case of solenoid, will always take Ampere loop in circumferential direction. And magnetic field, we are going to use mu naught and I inside the solenoid and 0 outside. Now let's consider we have to calculate what is the vector potential if we take the inside point of the solenoid. Now we have take the imperial loop inside the solenoid, its length of dl and radius r. So in cylindrical coordinate system, whenever we have dl vector in phi cap direction, so this is our dl vector. R define the phi cap. And our dA vector will be perpendicular to the circumferential direction. This is the area vector. And since this direction is the z cap direction, so this is our dA vector element, RD phi z cap. These things are given in Griffith's first page, just before the introduction. Like what is the DL vector and dA vector in different coordinate systems. So we have to calculate closed line integral A dot dl vector. So we take the imperial loop which is circumferential, so we can take mod A outside and we have to just integrate dl vector. And since we have d phi, so phi will vary from 0 to 2 pi. So this is this A dot dl vector. Now we have to calculate surface integral of B dot dA. We will take mod B since B and dA vector both in the same direction. So B dot dA will become mod B mod dA and mod B will come outside of integral. Now we have to integrate dr. Dr varies from 0 to the radius r of this circle and d phi varies from 0 to 2 pi. So we have to integrate dr and d phi. It will become r square by 2 and d phi become 2 pi. So we will take this quantity and we will take this quantity and equate them. So magnitude of A vector will become 1 by 2 R mod B vector. And we already know that the A vector is in the circumferential directions, that is the phi cap. So we can write A vector as 1 by 2 R B mod B is mu naught Ni inside case. So mu naught Ni R in the phi cap. So this is the vector potential inside the solenoid. Let us consider the case outside the solenoid. If R is the radius, so we have to take the imperial loop outside of this solenoid. This radius is small r. Our magnetic field is always going to be non-zero inside this region, which is inside the solenoid. So when we try to calculate S dot B dot TA vector, B to capital R magnetic field is finite and therefore we will integrate B to capital R the same way, but R to small r, that is this part, the magnetic field is zero. So when we can integrate this, it will become mod B vector r square by 2 into 2 pi. And now the left hand side, which is closed line integral A dot dl, again mod A vector came outside. R will not going to affect in this case. So it is 0 to 2 pi r d phi. D phi vary from 0 to 2 pi, so will become 2 pi r mod A vector. So we will have left hand side which is 2 pi r mod A vector and we will have right hand side which is pi r square mod B. When we equate them, this is our mod A vector. I have put the value of mod B vector here. And since it is in the phi cap direction, so this is the vector potential for the case when we are talking about the outside of the solenoid. So this is the formulation and we are going to use it repeatedly whenever we try to solve the questions. So let's move to the questions from previous year GATE exam. So this question from GATE 22 question, this question appear in GATE 2022 examinations. In this question, it is given that a current of 1 ampere is flowing through a very long solenoid made up of winding density 3000 tons per meter. Meaning we are given that the number of tons per unit length are 3000 tons per meter. So as in shown in figure, a parallel plate capacitor with plate oriented parallel to the solenoid axis and carrying a surface charge density sigma 6 epsilon naught coulomb per meter square is placed at the middle of the solenoid. So what is the momentum density of the electromagnetic field at the midpoint x of the capacitor? And it has to have the form of n into 10 is to power minus 13 Newton second per meter cube. And we have to find the value of n. See, in this question, we are given two conditions. We are given the solenoid, and we already know that. solenoid is basically talking about the magnetic field here. So magnetic field due to solenoid, we can calculate mu naught Ni since we are talking about the inside point and it is in the z cap direction. Now, if you know about the parallel plate capacitor, one plate carries a charge plus and another one carries a charge minus. And the electric field created by this parallel plate capacitor is from positive to negative charge. So if I take this as a x-axis, so our electric field is going to be, let's say, is in the x cap direction. And it is the electric field which is created by parallel plate capacitor, which is sigma upon epsilon naught. So we are given magnetic field, we are given electric field, and we have to calculate momentum density. So the momentum density P is given by S vector by C square, where S vector is the pointing vector, which is E vector cross P vector by mu naught. So if you wanted to know how this formula of momentum density and pointing vector frames, you can go through this NPTEL lecture in which this formula is derived. So basically, it's a formula-based question. We know our electric field, magnetic field. We can calculate S vector. We put this S vector inside this P, and this P is the momentum density that we have to calculate. So we started with the calculation of S vector. So we know that E vector and B vector are perpendicular. P is in this direction and E is in this direction. So whenever we calculate E vector dot P, it becomes mod E mod B into sine theta. Sine theta is the angle between E and B, which is 90 degrees. So its quantity is 1. So basically, it is mod E mod P by mu naught. So this is the magnitude of pointing vector. So mod E is sigma upon epsilon naught. Sigma is the charge density which is given to us as 6 epsilon naught. Epsilon naught will cancel out. We are left with 6. Magnitude of magnetic field is mu naught Ni and is the number of turns per unit length which is given to us as 3000. I is the 1 ampere. So we are left with mu naught into 3000. And the S vector is become mu naught into 3000 into 6 by mu naught. So basically it become 18,000 and we have to calculate the P vector, which is mod S vector by C square, which is 18,000 divided by C is the 3 into 10 raised to power 8 square. That become 2000 into 10 raised to power minus 16 or 2 into 10 raised to power minus 13. The unit is Newton's second per meter cube. So we have to compare it with the given answer, which is in the form of n into 10 raised to power minus 13. So that means n is 2. So we have to find the value of n, which is 2. So this is the answer for this question. Okay, now move to the next question. I hope you have cleared this question. We will ask your doubt later. So this question is from GATE 2018 exam. Consider an infinitely long solenoid with n turns per unit length, radius r, carrying a current I, which is alpha cos omega t. Alpha is constant and omega is the angular frequency. What is the magnitude of electric field at the surface of this solenoid? So in this question, it is given to us that our current is changing with time. So if you calculate the magnetic field, which is given by mu naught Ni inside and 0 outside, and it is in the z cap direction. So now our current I is changing with time. It is alpha cos omega t. So that means our magnetic field is also going to change with time. And whenever there is a change in magnetic field, it will induce the electric field from Faraday's law. And from Maxwell equation, curl of E is equals to minus del P by del T. This is the third Maxwell equation. We can calculate what is the induced electric field. And we have to find the magnitude of this induced electric field at this surface, that is small r equals to capital R of this solenoid. So Basically, if you wanted to calculate this quantity, what you can do is to take the surface integral on both sides, it will become curl of E dot dA vector, which is minus surface integral del B vector by del T into dA vector. And from Stokes theorem, it will become closed line integral of E dot dl equals to surface integral minus del B by del T dot dA. Now again we have to calculate this line integral E dot dl. So in this case, we have to calculate the electric field, our magnetic field in the z-cap direction. So let's consider a imperial loop inside this case, and to calculate the electric field at the surface in the letter, when we formulate it, we will put small r equals to capital R. So we will take the imperial loop inside this solenoid of radius small r, and this is our dl element. So we will calculate E dot dl as mod E. dl become r d phi 0 to 2 pi. And now surface area is again, this quantity will become minus mod of del P by del T into surface integral means 0 to R, RTR and 0 to 2 pi T phi. So when we calculate it, it will become mod E into 2 pi R minus del over del T of B is mu naught and I. And mu is constant, n is constant, it is I which will depend upon T. So this is only going to differentiate here. This will become r square by 2 and it becomes 2 pi. So we have 2 pi cancel out, I will cancel out. So mod E will become minus mu naught n del I by del T into r by 2. I is given to us as alpha cos omega t. So del I by del T will become minus alpha omega sin omega t. So we will put this into this equation and also put r equals to capital R since we have to calculate it at the surface. So it will become mu naught n alpha omega capital R by 2 into sin omega t. So we have, this is the magnitude of electric field. So we have to see if this option is available to us. In sin omega t, this option is there. So this is the correct answer. Now move to the next question. So in this question, it is given that it comes in K 2017, an infinity solenoid carries a time varying current IT, which is equals to alpha t square. So it means our current is again depend on time. The axis of the solenoid is along z direction. R cap and theta cap are the usual radial and polar direction in cylindrical polar coordinate system. Now we have to find the magnetic field outside this solenoid in terms of whether it is going to be zero or non-zero. So basically, we have already calculated that the magnetic field is always going to be mu naught Ni inside solenoid and it is going to be zero outside. And it is in the Z gap inside. And if you look at the magnetic field lines properties, it will be like this. So basically, it is zero mostly in this resin, but if you are talking about this Z direction, it is non-zero. So the component of magnetic field Bz, even with the outside case, it is not going to be zero. So Bz is not going to be zero, but all other case Br is zero and B phi is going to be zero. The change in current will only change the magnetic field value. It will not going to change its direction. So even though current here is changing with time, it will not going to change the direction. So magnetic field Br is going to be zero, P theta is going to be zero, but Pz is not going to be zero. So this is the correct answer in this question. Now come to the question from GATE 2015 exam. So in this question it is given that a long solenoid is embedded in a conducting medium and is insulated from that medium. Now if the current through the solenoid is increased at a constant rate, meaning the current rate of change of current is constant K. It will be some constant. Now, the induced current in the medium as a function of radial distance r from the axis of solenoid is proportional to. So, in this question, it is given that our current is changing with time with that constant rate. So, that means our magnetic field is also going to change in time, and change in magnetic field will induce the electric field into the system, and the induced electric field will create an EMF into the system, and the current I is given by the EMF divided by resistance. And therefore, if we know how our EMF is changing with time, we will get to know how our current is going to change in time. And the EMF is generally given by rate of change of the magnetic flux, del P by del T, and magnetic flux is given by surface integral of P dot dA vector. So basically we are, and since our area is not changing, our magnetic field is changing to the change in the current. So it will become minus del P by del T dot dA vector. So we already know that it is given by closed line integral of E dot dl from Faraday's law. So if we get to know how our electric field is changing with time, we will find how our current is changing with time. Basically, they are proportional to the same quantity. So first, by knowing how the electric field is changing with time, we can say how our current is changing with time. So we have to solve this equation again, and we have to find the electric field inside the solenoid as well as outside the solenoid. So let's consider first the inside case. So we have to take a solenoid, and we have to consider the magnetic field in this direction, which is the z cap direction, and we have to take an ampere loop inside. And when we take calculate E dot dl, it will become into 2 pi r for the inside case, and for the surface integral minus del by del t of mu naught ni dot dA. dA is RT phi. So let's say R is very from 0 to small r, pi 0 to 2 pi. So this quantity will become mu naught, and del I by del t is given to us that it is constant. It is become r square by 2 into 2 pi. So mod e into 2 pi r will cancel out. So mod e is vary as this quantity is constant. These are also constant. So basically it is varies as r bar proportional to r if we are consider the inside case. Let us consider the outside case. See, for the outside case, our magnetic field, when we try to take the imperial loop, magnetic field varies inside this region only. So when we try to calculate mod E into 2 pi r, this was integral 0 to 2 pi only valid from 0 to capital R. So it becomes del by del t. I have take little shortcut since I have already solved it earlier. So d I by d phi become minus mu naught del I by del t r square by 2 from this and 2 pi, and mod e into 2 pi r. 2 pi will cancel out. So mod e is equals to minus mu naught and del I by del t r squared by 2 and to 1 by r. This r. So all these quantity are constant. So mode of ease varies as 1 by r for the outside case. So our induced current will going to vary as R inside the solenoid and 1 by R outside the solenoid. So this is the correct option here. So with that, all the questions from this concept is solved. So if you have any doubt, you can ask me. So let me know if you are clear with this concept today.
Yes, I am clear.
Okay then. So basically, you are going to encounter this type of questions in the exam. And once you know what is the magnetic field due to solenoid, and how to solve the imperial loop and this equation, you can solve all the question related to this concept. Okay, then we will finish today's class early. So if you have any doubt, you can ask. Okay, then. Bye bye.
Thank you, man.